Hello everybody, my name is Nitye and today I'll be taking your lecture for ROS106. So today's workshop slash lecture will be based on URDF. So I think let's begin with first with what's URDF. So this is a document I will share after the lecture on the GitHub. So let's begin with this. So when you think of a robot, you think of wheels, a base, some kind of chassis, some kind of arms or something like that. So it's made of parts, right? It's made of links. Like suppose your arm is made of bones, cartilage, and muscles and everything. So in terms of robotics, we call these things links. Links are basically rigid parts of robots that are used to make bigger robots, right? So let's now move on to what is URDF. URDF is basically the description for what a robot is and how it is made. So, analogous to anatomy in humans, URDF is basically the order in which your robot parts are connected. Suppose, in terms of your human arm, shoulder is connected to a bone, and then the bone is connected to a further bone. That's how your arm is made, right? In URDF, that's what you define. It's basically a description format. The full form is Unified Robot Description Format. So it's basically writing instructions to build a robot. So it's basically telling the robot, telling the software ROS2 that my robot is like this. Because if you design a robot in CAD software or if you make a robot, you know what it looks like. The software doesn't. And if you want to visualize it or do any kind of coding on it, you will have to tell the software how it looks. So for that, URDF is used. So what URDF is basically is the recipe of what your robot is like. Suppose it has uh, it's a robotic arm that has three links, three solid cylinders connected by joints. So you have to specify what kind of links there are and what kind of joints there are and what positions there are at. So this data is essential for coding anything. If you try to make any kind of controller to simulate simulate the behavior of robotic arm, or you want to try to calculate the inverse kinematics or anything like that, so you'll need to tell the software what your robot looks like. So that's what URDF is used for. And I think let me show you a small demo as to what a URDF looks like. I think RViz was covered in one of the previous lectures. If not, let me cover RViz first. So RViz 2 specifically is a tool in ROS2 that is used for visualizing your objects or any kind of models you make. So if I run RViz 2 here, it should run in a second. I'm just in my default ROS check right now that we have been following for the whole series, and I have run RViz 2, and after a while it will just open this window. It takes a little while because it's a simulation thing, so it takes a while to load. So this is your RViz window. So right now you can't see anything on this, but if you make a URDF for a robot, you'll be able to see this. Now RViz is basically a visualization software. This center part is where the robot appears, and if you remember when we studied our TFs, you can also actually see the TFs in this window. After we make a robot, you'll be able to see the TFs. So let me, I think, show you a TF as well. Let me just stop this. And okay, so let me show you the demo for what we'll be making today. So this is a launch file I've pre-built and I'll share with you using GitHub, and then you can just see this is the kind of robot we'll be making today, and this is what it looks like in RViz. So if you can see these arrows, these are actually the transforms, the TFs that you studied about in one of the previous lectures, and these are the rigid links, the parts you can see. So suppose this is a wheel, this is the main body, this is a caster wheel, and this is the other wheel. So these are all separate links, and we'll learn step by step how to make this. And let me show you this as well. So when you try to visualize something in RViz, there's two things you'll need. So the first thing you'll need is the robot description. So what a robot description is basically what I've been telling you about. Robot description is the URDF. The software needs to know what a robot looks like and what its functionalities, what kind of links it has, what kind of joints it has before visualizing it. So that is one of the things. And the other thing it needs is the joint states publisher. So you see this small window, this is the joint states publisher. So what this does is it gives the states of the joints. Basically, if suppose it's a revolute joint, revolute means it supports rotation in one direction and no other movement in other axis, no other rotations and no translation at all. So the software needs to get this states of joints from you so that it can calculate the TFs. And you see this slider, this is a pre-built node inside ROS2, which you will call this whenever you want to just change values of joints. And you can also make them custom according to your use case, but for now we will just use the standard one. So you see this slider, if I just move this, you can see the wheel rotating, right? So this is what the joint states publisher is used for. And if I just use the center command, it will just put it to the center. So right now the limit of this joint is from 3.14, which is pi, to minus 3.14, which is minus pi. We'll come to the significance of this thing later, that I've just showed you, the limit thing. So now let's move on to what URDF really is, right? So I think you understand what it is, right? It is basically a description format that you use to tell the computer what your robot looks like, so that it can simulate it, and more importantly, it can calculate the TFs. So now what is it coding wise? So URDFs is actually just an XML file. Okay, so for now I've just pre-built all the code for this, and I'll just share that with you guys. So let me start from basics how I made this. I've gone into my workspace, then into my source, and I've made a new package called URDF demo. You can call your package anything, just remember the name of it. Now inside this package there's a proper structure of directory. So you see these 4 folders: launch, meshes, RViz, and URDF. These are folders you can't actually find if you just run ROS2 package create and suppose anything URDF tut. Suppose let me do this, and you can add the license and build methods, but for now I'm leaving them out because they are the standard methods. The default for license is Apache 2.0, and the default for build type is mintcmake, and I'll be using those two only. So I'll just use run this command, and then you can see this creation successful. Now if you go to this package, right, you'll see include and source, and you can't see in this. So what I've done is I've removed these folders because I don't have any use for them, and I've created these 4 folders because I need them. Now let me go through what these folders mean and why they are here. Okay, so this RViz folder is here because when you run RViz, let me show you again. When I ran RViz earlier, you saw this window, right? You see this thing, no TF data, and some kind of error. It shows an exclamation mark, right? So what happens is you need to change some settings in RViz so that you can visualize your robot. Now obviously there is the error that there's no robot to visualize, so it's obviously gonna give an error. But even if I give the robot description and the joint states to this RViz, it might not work because there are some configuration settings that you need to do. So what I've done is I've set the configuration. I'll actually put a small PDF for the steps on how to save the configuration in the GitHub, so you can check out the steps. But this RViz folder actually contains a config file for the RViz. So when you want to visualize your URDF in a RViz file, RViz window, you'll need this config file. Okay, so this is what it looks like. It's very like computery. So you'll find this in GitHub, and I'll put a PPT or PDF for the steps which you'll need to make your config file and how you can actually do it. And in the launch folder, there are actually 2 launch files. I'll come to the Xacro one later, this display_Xacro one later. In the basic launch file, what I've done is, you know what, let me just explain what kind of nodes we are using. So as I said, when you want to visualize something in RViz and you want your RViz to calculate TFs, that is one of the main use cases of RViz. It can calculate TFs for you. So for a small recap, TFs are basically the relationship between links, and they are in real time. So if you try to move a wheel, so the TF for the wheel with respect to some origin, suppose a box like a base link, right, that changes. So instead of manually calculating that, RViz calculates that for you based on the joint state. So if you move the wheel 1/4 of a turn, which is pi by 2, so it will calculate the corresponding TFs for the wheel and publish them to RViz so that it can visualize the change. So when you run RViz, there's a few things you need. So the first thing is this is the basic RViz node, right? This is the RViz node that you'll need to run for opening the RViz window. And you see this thing, RViz config, this argument. So what this does is it uses this config file in the RViz folder, and it gives it to the RViz node so that it can open the already set settings, right? So that it doesn't produce an error when you try to visualize it. So this is the method to do it. This is how you actually give arguments in this XML launch files, and these are the variables that store the paths for them. So you can create variables in your launch file in the XML launch files using let, and this is the syntax for it. You can name the variables and you can put the value. So let me come to this find package share URDF demo thing. What this does is this function thing, find package share URDF demo, tells the path for the package URDF demo to the file. So you don't have to actually manually write the you don't have to actually write the manually write the path for the package, and you can just write this and it will pick up the path from that. This is just a standard thing. And after that, after coming to the package, in the URDF folder I have a few files, and the main one is my robot.urdf. For now the convention is to just name your robot and put a .urdf in front of that, and that makes your URDF file. But I'll come to that later. I'll just explain what you need to launch to visualize in RViz. So there's 3 things, right? This is the RViz node that you need. This is the this basically opens the window that you just saw. And in the joint states publisher, this is the pre-built joint states publisher GUI, the slider window that you saw. What this does is it takes all the joints and creates sliders between the lower limit and maximum limits, and then you can just put the sliders at the position that you want, and this sends the joint states to the RViz. And in this thing, this is the main thing that we will need. This is the URDF publisher. So what this does is robot state publisher is a pre-built node in ROS2. The param thing is the main thing. See this robot description, that's what I was saying, that you need to provide robot description and joint states. So robot description, you provide URDF. So this is the syntax for providing the URDF to the launch file, and you can see the value of URDF path here. Okay, so this is the basically launch file you'll need to visualize any URDF you're making. And this is a good practice to build a launch file in your package when you're making the URDF, so that when you make any kind of changes in your URDF, you can visualize it. And what I mean by that, you'll understand in a bit. For now, just bear with me, and let's now actually begin with the URDF. Okay, and I'll come to meshes later. So these are I explained RViz and launch. Now let me come to URDF. So this folder contains the actual URDF we are about to make. So this is what a URDF looks like. It is basically an XML file. XML is just a markup language. I think some other markup languages you have come across are YAML and maybe HTML, of course, if you have dabbled into website development or anything like that. So this is the standard things. This is the standard way of starting a URDF. You name it anything you want, and then you put a .urdf at the end. So this thing is always necessary at the beginning of your URDF. This is just standard. It tells the system that you are using XML, and after that you create a robot tag, and everything that you want to tell about the robot, any kind of description of the robot, you'll have to put between this robot tag. Alright, and you can name it my robot. The significance of this is not that necessary, but basically when you use it in other suppose simulation engines like Gazebo, this is the name that will come up. Okay, so let me go step by step. Sabse pehle I'll go to the link. So this link thing is what is important. Alright, there's two main things contained in a robot: links and joints. Links are basically the rigid parts of the robot. Suppose a wheel is a link, and suppose a solid cylinder that is connected to a joint, the cylinder is a link, and the whole chassis can be considered a link if it doesn't have any joints. Any rigid part is called a link. Okay, and by convention the base link is the first link that you make. It can be your chassis, it can be, suppose if you're making a robotic arm, it can be the base of the arm, but base link is the base link is the conventional first name to given to the first link. Okay, now let me come to the inside tags. So the link contains actually three kinds of tags. You see this: visual, collision, and inertial. Now let me show you what each of these means. So visual model versus collision model is one thing. So visual model is basically what your robot will look like in RViz. So suppose if you are making, let me take a complex project. Suppose you are making a robot dog. Okay, so what will it look like? It will have its proper legs, it will have its body, it will have some other electronic components and everything like that. And in the legs there will be like bone structures, right? It will be a thigh, and there will be like the calves. So you want to visualize it well, right? You want to see what the robot will look like actually when you make it. So this is the place you'll put it. You can actually use just basic shapes: a box, a cylinder, and sphere. These can be made in the URDF only. I'll show you how. But if you want to suppose make it complex, if you want to input a complex shape into the URDF, if you want to visualize a complex shape, you can do that as well. For that you will need to use the meshes folder. In the meshes folder you can upload STL files, and in the visual tags you can specify that this looks like this STL. So you can visualize that your part looks like the complex part STL that you have uploaded. Alright, I won't be able to show you the demo for that. I haven't prepared that, but I'll share a document on how to use meshes or how to use visual tags to visualize complex parts. Okay, and let's come to the collision model. Collision model is basically a simpler version of the visual model. So what it does is, collision model, you provide the basic shapes the robot link looks like. So suppose you have a chassis. It's a suppose 4-wheel drive robot, basically has 4 wheels and is rectangular. So you give the collision model a proper box that encapsulates your visual model. Suppose your visual model is not exactly a rectangular, it suppose has some complex shape around it. So you can actually make the visual model to be complex, but it is conventional and it is just a good practice to make collision models as simple as possible, because if you don't, it will basically take a lot more resources, and the computer will have to run a lot more calculations to figure out if this part is colliding with something else or not. Collision model basically refers to if something is coming in that, suppose you try to simulate a robot. If it falls to the floor, if you don't provide a collision model, it falls through the floor because it doesn't know that the body has to collide with the floor, right? So that's what collision models are used for. The body has to collide with other bodies, other links, right? So that's why collision is used. And if you give it complex shapes, it will have to run a lot more calculations to figure out if it is colliding for this. So this is the crux of it. No fancy details, just tells the computer don't let things pass through here. Okay, so and let me come to the third one. The third one is inertial tag. So in the inertial tag you give it details like mass and its inertia. Inertia is basically the moment of inertia, rotational moment of inertia. So the theory of it is quite complex. I can't get into that. If you are from IIT Delhi, you have probably learned about this in APL 100. And if you're not, you might want to search about moment of inertia and what these components actually mean: Ixx, Ixy, Ixz, and everything like that. So basically, inertial model is used for when you simulate it. You'll have to have mass and inertia, according to which you'll have to give it forces and velocities and everything. So this is needed for all the calculations that the physical engine does. Suppose if you want to simulate your robot in gazebo, which will be a further step, you need inertial tags to know how much a part weighs. Alright, so that is the basic information about what a link contains: inertial, collision, and visual. Okay, so let me do one thing. Let me cover this whole thing and then I'll show you this in the RViz. So let me come to the material tags. This material tag that you see, it's used for making colors and some other things, but for now it's only used for colors. So this is how you actually create colors in the your URDF. So when I showed you the demo, you could see there was a green body and there were gray wheels. So this is how you create colors in the URDF. Otherwise, if you don't create colors, all the links will look the same color and you won't be able to differentiate them properly. So it's a good practice to create colors and give them to the visual models. Alright. So this is the syntax for creating colors. You open a material tag and then inside you give a color tag. So RGB, means R means red, G means green, B means blue, and A is basically the opacity. So one means it's completely blocking, and if you give it a lesser value, it will be slightly transparent. Okay. So now let me come to the visual model for the base link, and we'll see how to actually make the robot. Right. So inside the visual tag, you open the geometry tag, and inside this you can define a box. Suppose if you want to make a cuboid, you can define a box and use the size commands to give it x, y, and z dimensions. You can also use other kinds of basic shapes, like in the caster wheel link you can see this sphere and you can specify the radius, and there's another basic shape, cylinder. So you can make a cylinder using the radius and length commands. You can give it the radius and length argument, sorry. And then I come to origin. So let me explain what origin is. When you are calculating TFs, you calculate with respect to a frame, right? And frame has an origin. Now compared to that origin, the visual might be same or different. Let me explain it like this. When you see a box, it has a center, right? That is considered the origin of the box. Suppose I am considering that is the origin of the box. Now that origin and the frame of the link, right, that is used to calculate the TFs, might be same or might be different. So this origin tag actually gives the displacement of the visual origin from the frame origin. So if you want, suppose you are building a robot dog, and the point of interest for you is the bottom of the box, right? So you can actually make the TFs according to the bottom of the box, and then you can change the visual so that the box appears above that. So this is that it might be a little confusing, it might be a little bit confusing. I'll suggest you to change the values of this and try to visualize it. You'll understand it a little bit better. And then below that you can see the material name green. So this is where you put the color. So you can see we defined the color green here, and now we just call it here to give it the green color. So that marks the end of the visual tag. This is basically what will look like. Fine. So this will make a box that is green in color, that has dimensions 60 centimeter, 40 centimeter, 20 centimeter, and the Z is shifted by half of it. So basically the box, the frame origin is suppose at 000, the visual origin would be at 000.1. So the frame origin will be at the bottom of the box instead of at the center. Okay, so this is the significance of the origin tag. And this RPY is actually roll, pitch, yaw. These are the Euler angles of rotation. RPY means rotation about x, y and z respectively. Roll, pitch, yaw. You'll see the significance of it when we make the whole URDF of the robot. And for now we'll just use 000. Okay, and now let me come to the collision tag. It also has the same structure, geometry and origin. There's no need for the material tag here because the collision doesn't need to be colored. You're not using it for visualizing your robot, right? There's no need for it to have a color. The box is given same. Suppose if we make a complex shape, we might want to simplify it. Suppose I make a complex chassis, we can simplify using here, using the box tag here instead of the mesh tag. So I'll upload a doc how to use meshes. Instead of this box, you can actually use a mesh tag and give it the file path through this meshes folder. Okay, I'll upload a PDF for that. Now the origin actually is the same as the visual tag. You can usually use the same values as the visual tag, but in some cases you might have to change them, but they are too complex for our use cases. So for now we'll just use the same values. Now coming to the inertial tag, again origin tag contains the same values as in the previous ones, and in the mass value you can specify the mass of the body. I've specified 10. These values are a little bit arbitrary. You can change them, it won't matter right now. If you try to simulate it in some kind of physical engine, this will play a big role. And in the inertia tags, these IXX, IXY, IXZ are the moment of inertia components. You can search about them if you want to study in detail, but for now I've just put values here. So actually when you are making a URDF, you can actually give it the dimensions of the boxes or cylinders or spheres you are using, and there are formulas that exist that help you calculate these inertia values. But I'll come to that later. There are better ways to calculate it. For now I've just calculated it manually and put it in the arguments, but there are other ways to do it. Okay, and this is the similar thing. I've made another visual tag, a sphere, and then specified all these things, and then I've made the collision model and the inertial model. And now I'll come to another important part, which is joint. So in the joint, what happens is, for calculating TFs you have to make a proper TF tree. Basically no two links can be free. One link has to be a child or a parent of the other. If you are making more two links free, the RViz will give an error because it doesn't know which is the main link. So that's why you usually name first link base link. It's usually the parent of most of the other links. It is the ancestor of all the links. So in the joint you can actually define the parent-child relationship between two links. So what you can give a joint name. You should always give a joint a name, and you can actually give it a type. So there's a few types of joints. For now I'll be using fixed, but other types include revolute, prismatic, continuous. So revolute allows rotation in one axis, prismatic allows translation in one axis, and continuous is just revolute, but it is used for wheels. So basically wheels don't just move between a limit, right? They have to continuously move. So that is why there's a different joint type called continuous for them. Okay, so and fixed is basically just fixed, it doesn't move relative to the links. Okay, and a good convention is just to use, suppose the base link and caster wheel link are my links. So I've used the base caster wheel joint for this, for the name of this joint, and then I define the parent and then the child and the origin. So origin is basically the displacement of the joint origin from the origin of the parent. So suppose I have a box and I have to make the, suppose I'm connecting a wheel. So the wheel has to be connected on the bottom, suppose one corner of the box. So I'll have to make the joint at that corner instead of in the center, because the wheel has to rotate respected to that corner, if that makes sense. Basically you just define the position at which the wheel will move. So that's where you define this. Okay, you can play around with this joint value, the origin values in the joint, and you'll understand it better. All the main thing about URDF is you'll have to play around with the values to understand better. Okay, I can teach you how to, I can tell you how to make things, but I can't show you every case for the visualization. That would make this lecture a lot longer. So I'll request you to just mess around with the values of this origin and RPY again, and you'll understand it better. Okay, so let me show you this in the RViz, and then you'll have a better idea about what this URDF looks like. Okay, so now I'll just call con build once because I've made some slight changes. The changes I made are actually in the launch file. So in the launch file that you see here, I've actually changed this to two links. Before this I was using the other URDF for my robot that contains the URDF for the whole robot, but let's start with just two links and you'll be able to visualize it better. Okay, I'll just source my environment again. And now I'll just run my file ROS2 launch URDF demo display. Okay, so now this will run an RViz instantiation. This takes a little while. So this is what the robot looks like for now. Okay, these are the two links that you can see. There's actually three links because I've created one dummy link in this base footprint. If you let me go to my URDF, and then you will be able to see. If you can see this one line of code, this link base footprint, it doesn't actually have any visual tags, it just has a frame. So that is used for other kinds of use cases. When you build a robot, it's a good practice to build a shadow, basically a shadow link that points to a point of interest. Suppose you are making a mobile robot, so you need to usually map where it is going. So for that you need a point to locate. So this base footprint will be that point for me. Okay, so these are the two links that you can see. This is the base link and this is the caster wheel link, and you can actually also see the transforms. Okay, so for now these are actually fixed. So if you see the joint state publisher, it's actually empty, but if you put revolute or continuous or prismatic joints in, you'll see sliders like previously. Okay, so this is the visual model. You see this visual enabled, this is the visual model. If I turn this off, you can only see the transforms. These are the transforms, these are the three frames, and these are the transforms. Okay, now the importance of collision can be seen here. So this is the collision model. Okay, this model is not usually visible, it's usually only visual, but the collision model contains the information of don't let things pass here basically. Okay, and you can also visualize the inertia, although the inertia is slightly off. I think might have messed up the values a little bit. Again, I'll give you the formulas of how to calculate them, and you'll be able to calculate yourself. And you can see the inertia blocks, and if I disable collision, you can see the inertia. So this is how the inertia looks like. Okay, so this is what a URDF basically looks like. Now this can be quite a lot to comprehend, so let me just give you proper steps on how to build a URDF. You first start with a link, and then you make a second link. After making the second link, you can create a joint between those two. And within creating a link, the first thing you do is create a visual model. Then you fix the origin. So how do you fix the origin? Let me actually show you what happens if I change this. That will give you better perspective. I've changed this to 0.1, right? In just the visual one, I haven't changed it in the collision ones. So let me just build it again and source it again so you can see the difference. So I'll source it, and then I go to my launch file again. Okay, so now this opens. Now you can see the caster wheel is actually inside this, right? So you can see the change. You see the frame's origin is at the center of this cube, right? This is the frame's origin, and the visual origin was previously set here 0.1 above this, but now it's at the same location because it's 0, 0, 0. So now you can see the difference. Now if I enable the collision, you will be able to see it more clearly. So if you remember, haven't changed the origin for the collision. So the collision origin is here 0.1 above the frame origin. So that's the importance of the origin tag. Okay, I hope it is clear now. I'll just close this and change it again. So that's what I mean by fixing the visual origin. You make it so the visual is according to the TFs that your use case is. Okay, I understand that might sound confusing. Basically, if you're making a mobile robot, it is a usual practice to keep the box above the TF frame. Okay, and if you're making, suppose, a robotic arm, it is a good practice to keep the TF, the suppose cylinder is above the frame, so it's easier to visualize instead of at the center. So let me change this back to 0.1, and I'll move to other things. Okay, so I think you understand these steps. I'll put a document explaining these steps again. So the basic steps are: create one link. Okay, start with the visual tag, then you fix the origin of the visual tag, then you create collision models, and then you create inertial tags. Okay, so this completes making one link. Now similarly, you can make another link using the same steps, and after that you make a joint between them. Now to show you the importance of the joints, let me comment this out and try to build this and show you what happens if you don't make a joint. So what this will do is actually break my code. It won't actually work. So you see this gives an error, and if you go to this window, you will find the error somewhere here. Error failed to find root link. So you see this error. This basically means it doesn't know what is the root link. It doesn't know where the TF tree starts. According to it, there are two roots which can't actually happen. So that's why you always have to define joints between two links. And this is the joint for the base joint between the base link and the base footprint. Base footprint is the shadow link that you saw that is used for advanced concepts. We'll see it in further workshops probably. So these are the main steps: make one link, make second link, make joint. and then you fix the origin of the joint. Okay, I'll note these steps down, and you can follow them to make any kind of complex robot. So if you're comfortable with making two links, now I'll move on to this big robot. So what you can see, base footer, base link are the same. Now I introduced a secondary link, which is the right wheel link and the left wheel link. So these adds the wheels. So you can actually look at the visual tags. It actually uses a cylinder here, and even in the collision tag I've used cylinder. There's one more thing you can do, one more improvement in my code. Uh, when you're making wheels and you're specifically making collision models of them, you can sometimes replace cylinders with spheres, because when you try to simulate it in a physical engine, if there are more points of contacts with the ground, sometimes it can behave weirdly. So one thing people do sometimes is change this cylinder to actually a sphere of the equivalent radius. So it actually only has one point of contact with the ground, and in terms of visuals it can stay the same, but when it comes to the simulation of friction and physical moving of the board, it actually helps a lot. Okay, so I haven't changed that right now, because that might be a little bit confusing for others. So I've just kept it cylinder, but that is one thing you might find in some URDFs if you open them. So one common thing is, people don't usually build URDFs by hand. They usually look for URDFs pre-built, available on GitHub or other platforms, and then they modify it according to their needs. And in some softwares like SolidWorks, you can actually convert your CAD files to URDF directly, so you don't have to write all of this by hand. But you should know how to write it, because if there's any kind of issues, you need to know how to debug them. Okay, so here you can see in the R I have specified 1.57, which is actually pi by 2. So what this will do is, I'll show you what happens if I don't do it 1.57. I'll show you, but for now I'll just continue. In the inertial tag, again I've defined the origin, the mass value, and the inertia. Okay, the left wheel is same. Now coming to the joints, you can see these two new joints that connect the left and right wheels to the base link. So now you can see the origin is at the location of the point where the motor would be in an actual robot. So that the joint should be where the actuation has to happen. So actuation is the rotation of the wheel in this case. So it has to happen corresponding to the edge of the robot, right? It doesn't have to happen at the center of the robot. So that's why you have to specify these values, so that it happens relative to the edge of the robot instead of at the base. Okay, and in the axis, now here you can see actually continuous type, right? This is basically a rotation in one direction, and this is the axis defined for that. It will rotate about the y direction. For both these, you can see the same things. Okay, the rest of the things are the same. So let me change the two links to my robot.urdf again. So if you're making any kind of URDF, you can use this exact same launch file. You just have to change the name for the URDF and make sure it's in the URDF folder. Okay, now I'll just have to build and source my environment again. Build, source, and then I'll just launch this, and then you'll be able to see this whole robot now. Okay, now you can see joint state publisher actually has two sliders, like we saw in the beginning of the lecture in the demo. So these are the two new wheels added. So you can actually see if I can rotate it using the slider. So actually what happens is, in you see this minus pi to pi in the continuous one, there is not it is not defined for infinite slider. You can't obviously have an infinite slider, so it's actually defined for minus pi to pi. Okay, so that is the significance of this minus 3.142 and plus 3.142. So if you are making a revolute joint, you have to specify limits and suppose you specify -100 degree to +100 degree, so you'll see the corresponding values of in radians here, which it will be between -100 to +100, and it can be converted to radians, and you can find the value here. Okay, so this is what the robot looks like, and then you can see the collision as well. This is what the collision model looks like, and if I show you the inertial properties, this is what the inertia looks like. Okay, so let me show you what happens if I don't rotate the r by pi by 2. Okay, so let me go to the wheel link. I'll change this to 0. Okay, then I'll just build never mind, my bad. I'll build source and then run. Now you can actually see what happens. So you see this is what happens if I don't rotate the origin. It actually becomes flat, which removes all kind of functionality from it. So you see these three axes, right? R, G, B, X, Y, Z. These are this is what these axes represent. So I have to rotate the wheel 90 degree about the R, which is X, and X is roll, which is R. Okay, so that's why I specified 1.57 here. I hope you understand the significance of this. And one important note, when you specify RPY, it happens in that order only. So suppose you rotate 90 degree in X and then 90 degree in Y, it will have a different result, and as opposed to rotating in 90 degrees in Y then 90 degrees in X. So you'll have to be careful that it happens in this order only. Okay, and same with XYZ, it happens in this order only. Okay, so that covers the basics of URDF. I hope you understand what URDF is and what is the need of it and how to make one. So I'll obviously upload all the codes and everything so you can understand it a lot better. So now that we have covered the basics, let's cover a slightly advanced topic in URDF, but not that advanced, but it is a very useful thing. Now we'll study about Xacro. So Xacro is basically something ROS2 functionality, let's say, that allows you to make your URDF a lot easier. So we are programmers, right? I think most of you have programmed something or the other. The best thing about programming is variables and functions. They are the most used things in programming. Imagine having to write every single thing at its, like suppose not having functions. You'll have to write a whole block of code every single time you want to do a very simple task. So that's what Xacro does. Xacro introduces variables and functions in URDFs. So using them, you don't have to actually do the whole process of writing. Let me show an example. Like you see this left wheel link and right wheel link. So you see it's pretty much identical except for a few places. Let me see any place. In fact, it's actually identical. The difference is in the joint. So you see these are identical. So the only difference is the name, right and left. So I don't want to have to write this again, right? I can obviously copy paste it, but again that just makes my URDF a lot longer. So that's why we use Xacro. So when I use Xacro, it gives me two things. It gives me Xacro properties, which are actually variables, and it gives me Xacro macros. Xacro macros are actually functions. So let me show you how to use Xacro. So when you want to use Xacro, you actually use this argument in your robot tag. This is just something you use when you want to use Xacro, and let me show you some other files as well. So you see this myrobot.urdf, right? So this is quite long. Now I can actually divide this in a little small files, right? So I've divided it into 3 files. So what this Xacro also allows me to divide my URDF into files. So I can actually include other Xacro files in my main Xacro file. So this is supposed to be my main Xacro file, okay, and I have included these two Xacro files in my main Xacro file. So you can actually see the name is a little bit different than before, right? Before I was using myrobot.urdf. Now I'm using myrobot.urdf.xacro. So when you are using Xacro, you have to ensure that .xacro is at the end of the file name. Now let me go to the other files, but before let me explain how to include other files. So this is the syntax of including other Xacro files in a URDF file. So why I have done this, you'll understand when I show you the contents of these two files, but this is how I've included two other Xacro files in this. So you can actually see this find URDF demo, like in the launch files you could see find package share URDF demo. So this also does the same thing. It actually just finds the package and then goes to URDF and then goes to this file. So now I'll go to common properties. So what common properties contains is the material tags, the color tags that are used, and these are the most important functions that you'll use. Okay, so I've actually defined three functions, three Xacro macros that actually enable me to calculate the inertia values using the dimensions of the boxes / cylinders or the spheres. I don't have to manually calculate and give the values of IXX, IXY and IZZ and all the other components. I can just give it these values. So you see the parameters. I have to give these parameters to the Xacro macro, which is the function, and it will calculate my inertia values, and it will add that to the link. So you see this tag. All of these things inside the tag will be added where I call this function. I'll show you where I've called the functions when you so you'll understand better how I've called the functions. But this is how you define a function. You have to give it a name, and you have to give it the parameters that you have, which is basically the variables you give to a function, right? So these are the parameters, and then to use these variables, this is the format. Use a $sign and then curly brackets, and you can just write normal any kind of code you want. So you can actually write this thing as well. You can write formulas inside arguments. Okay, so you can see these three functions. You can look up the values of IXX, IXY and everything like that. These are the formulas for the boxes, cylinders and spheres. Okay, so these are very useful because now I don't have to actually calculate my inertia values. I can just give it the mass and all the origin values, and it will just do it for me. Okay, so I've defined these here, and another thing to note, I've added this tag in the robot tag. So one thing to note also, in all my Xacro files as well, I've started this robot tag, and all the coding I've done between them only. Okay, so now I'll go to the mobile robot. So here you can see a Xacro property. So if you are making a robot and if you want to change the size of it, when you're physically making it, of course it's a lot difficult to change the size, but when you're trying to simulate it, it's easier to change the size. You just have to find the dimension where you have defined it, and you have to change it. So to make it even more easier, you can just define variables at the start of your file, and then you can call these variables anywhere you want. So you will see where I've called other variables. So this is how you define a variable. Use the Xacro property and you name it and give it a value. Okay, so this is how you define properties, and you can actually see I've defined a Xacro macro here as well. This is for the link. Okay, and now let me show you how to call a Xacro macro. Okay, you see this line of code. This is actually how you call a Xacro macro. You can see how I've defined a Xacro macro called cylinder inertia here, right, in the common properties. Now when I go to mobile robot, I can actually call this Xacro macro to calculate the inertia. So this is how you call it: Xacro colon the name of the Xacro macro, which is the function, and then you give all the parameters values in this format. Okay, and again these are how you use variables. So I've defined these variables here, Xacro properties, and then I can use it in the whole document using $sign and then curly braces. So I can just change any kind of values I want from here instead of actually changing it everywhere manually. And another thing this introduces is pi. So right now I have been hard coding the values of pi, right, 1.57, but now you can actually use pi keyword, which is pre-built in Xacro. You can use the pi keyword and divide it by anything or multiply it by anything to make any kind of angles, because all of these angles are given in radians, and you can actually give it in degrees and just create a function to convert it into radians. So that also helps. Okay, so this is how you call a Xacro macro, and let me show you one another example. Here I've called this Xacro wheel link and given it the parameter of prefix. So here you can see I've defined just one parameter prefix and I've used it to name the link. Okay, so this is how you use Xacro properties and Xacro macros, and it actually drastically helps you because it reduces your code and it makes your code more modular. And again, you don't have to actually manually calculate values. This just does it for you. So this is how you make a Xacro files, and this is how you use Xacro macros and Xacro properties. So the other things are just completely same, and the only thing that changes in the launch file. So I've created a different launch file for the Xacro files, but you can just change it here as well. The only differences are here. When you're providing the robot description, you use the command Xacro instead of cat, that like we used here. Okay, so you use command Xacro to give it the URDF, and here you name it .Xacro. Now if I just call conbuild real quick and show you the Xacro URDF, you'll actually see it's completely same to the normal one, but it helps a lot when you're making a big robot. When it has a lot of repeating part, the macros actually help a lot. I would suggest you try to build a URDF from scratch. That's how you'll learn the best, and you can also tweak values of origins and everything, and that's how you'll be able to understand everything better. So I'll just build, and let me source this, and now I'll, instead of display.launch.xml, I'll display Xacro1, and now you can see this will actually give me the exact same robot. But here the difference is, you remember I made some mistakes in the inertia, right? In this one I didn't. The inertia is actually perfectly fine and as it should be. If I disable the visual, you will see this is better, because now it reduces human error, right? I don't have to calculate it manually and make a mistake. It does it for me. And if I enable collision, this actually does what I was telling you. This uses spheres instead of cylinders for the wheels. So again, this is optional right now, but when you try to simulate your robot in physical simulation engines, it sometimes helps to use spheres instead of cylinders. Okay, so I've given you both the codes. You can choose what you want to do, and again, it's a better. You can tweak everything and you'll learn better, of course. And here, of course, you can see the joint states publisher. So this is my complete URDF, and this is how I visualize it. Okay, so the steps remain the same. Start with a link. Inside a link, start with a visual tag. Inside the visual tag, make the box, then fix the origin, make the cylinder or whatever you want to make, then fix the origin. Then you make the collision model, use the same origin values. Then you make the inertial model, and if you have defined Xacro macros, which I suggest to do in all your projects, in all your URDFs, it really reduces the time it takes. Then you call the Xacro macro or define the inertial tags and give it inertia, and then you make another link in the same way, and then you make a joint, and you just keep on following these procedures to make other parts, and then your robot is ready. So this was us making a mobile robot, and I suggest you go through all the codes and try to do it from your own on scratch, so it will help you learn a lot better. And again, let me show you one more thing. If you remember, we defined the y-axis for rotation in the wheel joints, right? So when I try to rotate, let me rotate this one. So you see it's actually rotating about the green axis, which is the y-axis. RGB, G stands for y. G is green, G stands for y. Okay. So this marks the end of our lecture. I hope you understand. If you have any questions, you can text us on WhatsApp or reach out to us. And all the codes and everything, all the documents used will be available on GitHub. And this lecture recording will be available on the website. So thank you for tuning in. This marks the end of the lecture. Thank you.